Alright, we're continuing our journey with circle proofs, and we're looking at cases when there's chords present in circles. And this video is going to cover Theorem 8 and Theorem 9. You can see then, so you should pause the video and get a copy of those. They'll make more sense when I demonstrate with the aid of a diagram, but briefly, Theorem 8 says if A, B and CD are two chords of a circle that cut at a point P. Now that P has two cases, inside and outside the circle. So we're going to look at both cases. Then PA times PB equals PC by PD. Alright. Theorem 9, if P is outside the circle, TA and B are points on the circle. PT is a tangent, PAB is a secant. We can see that PT squared is PA times PB. So they're our last theorems we're going to learn in this unit of work. So to prove Theorem 8, we'll have a look at the following. So remember, case 1 is inside the circle and there's a second case outside the circle for point P. So we have two chords according to the theorem, AB and CD, and they intersect at P, which happens to be inside the circle. So we're looking at triangles. There's two of them, and I'll shade this one in, which is called APC, and the other one DPB. You'll remember that vertically opposite angles are equal, and we have vertically opposite angles here at APC and DPB, hence they're equal. We also have CAB, which I'll mark in. Alright, and we have BDC. Okay, so both of those marked in. Now they're angles in the same segment. Let's have a look at that. This actually comes from Theorem 2. So angles in the same segment are equal because the segment would be using the zone here, which finishes at CB, and we have an arc here. And remember, from what we know from Theorem 2, that we could put in last time, if you look back at Theorem 2, we used point E, and we've got an angle. It's an example of an angle in this segment here, which I'll shade in lightly. Better put in the other chords actually. Do that. Okay, basically I'm just repeating segment 2. So you would say angle E. Angle E is an angle. So angle E is a segment in segment of the same name. So segment CEB. Well, angle E, or angle using the full name, angle CEB. Sorry, that B didn't turn out very well. There we go. So angle CEB is an angle in segment CEB, but it's just one possible angle. You can also see that this angle here is another example. Alright, so you could say the same thing. You could just replace CEB with CAB. You could also replace it with the other one we're looking at, BDC, which is here, BDC. We were looking at that a minute ago. Rewind the video if you lost track of that. Okay, but they're all in the yellow segment. Alright, so we could replace that with the other one there, BDC. They're all angles in the segment, so they're equal. Alright, So back to theorem 2 for that one. Remember, the yellow, it shows the segment that they're common to. So this is application of the theorem 2. So moving on with the proof here. So we got up to that bit there. Angles in the same segment are equal, and thus we have triangle APC. We have triangle APC. Let's trace that out. Triangle APC is similar triangle to DPB. That would be according to the three angles being the same. Thus their corresponding sides are in proportion, so PA to PD. So if we look at PA compared to PD, that would be the same as PC is to PB. So remember, similar triangles have the same shape but not necessarily the same lengths. Okay, so we can look at the proportions of the corresponding sides, and if we cross multiply or rearrange, we've got that proven. Case 2 is the same, but it's outside, and the intersection is outside as per that diagram there, so we would have similar working there, but PA is to PC, is equivalent to PD is to PB. We can do that because we can show that APD, the triangle, whoops, I've overshot it, APD, is similar to CPB. I think I'll just clean that up. So I've traced those in, and we rearrange and can basically do what we did above. So you'll probably need to go back and have a look at the steps that weren't shown there, but they are in the same vein as case 1. You'll need to go through those and find angles that are the same. So for theorem 9, we need to locate a point P outside and draw that situation where we have TAB are points on the circle such that PT is a tangent and PAB is a secant. Alright, so theorem 9 to finish off. Okay, so we draw as described, and we commence work on that. So we've got ATP, which is there, alright, equals TBA, which is there. You'll remember the alternate angle theorem that said this angle here, well, I wanted a different color. This angle here is equal to any angle subtended by chords inside the segment. Okay, we can see that if we're talking about a segment, we're talking about this here. So you need to go back to that alternate angle, that alternate segment theorem. Okay, so the segment's been highlighted to assist you there. Okay, so that's why those two are equal. PAT equals PTB. Let's have a look at that. PAT, that one, equals PTB. Let's tidy that up. PAT equals PTB because this is a common angle here, and if you think about it and have a look at the color coding I've put in there, we've got if I go in reference to colors, we've got the purple here, or rather I should start with the orange, we did that one first. So the orange here, they're equal. Yellow's a common angle, so yellow's common angle, so they probably should have wrote that in, common angle. And notice that I'm comparing using big triangle versus little triangle. So let me get a different color here. So the big triangle PTB versus the smaller triangle, put in blue, PTA. In both of them we're summing the angles, so in both cases they need to equal the same thing, 180. So A is common, as I said, and we looked at orange being the same, so we've got see how we've included 1, 2 angles in each of the triangles now. So we just got the purple angles. Let's put them in again. The purple angles PAT and PTB, they have to be equal because they all equal 180, you see, so they are equal even though the diagram doesn't look that way. Therefore, according to AAA again, so I'll make sure that's put in there, that's the reason, the two triangles with the same names are similar due to angle, 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 and we can compare their proportions together. PA along here in regards to PB is the same comparison, so PT, that and that is the same as PT over PB. And we can rearrange that, again cross multiply or rearrange, and you get that there.